Okay, good morning everybody. We're going to start off today by sort of finishing off the last part of the last lesson, which I wasn't able to quite get to. And then we're going to try to make it through all of the following 4.2 lesson, because it is a bit thinner in terms of content. Okay, so let me just remind you what we were doing. We started off by trying to come up with a sort of calculus way of finding when a function has a minimum, okay? And so, it's all well and good when you have the graph. You can just look and see, aha, there it is. That's the minimum right there where we hit the bottom, right? But what if you don't have the graph? Okay, if you don't have the graph, we want to describe some sort of analytic calculus techniques which we can use in order to find the x value of this minimum. Once we have the x value, finding the actual point at which this thing reaches a minimum amounts to just plugging that x value into our original function. Okay, so our initial hypothesis was maybe it happens when the derivative is 0. And that was certainly true for this case. When the derivative became 0, that was when we hit a sort of turnaround point. Could be a min, could be a max. But that wasn't completely satisfactory because we have cases such as these absolute value functions, right? So we had to expand our understanding a little bit to incorporate these special cases. Okay, so our working theory after that was that a minimum, should it exist, will occur at a critical point, where a critical point is defined to be a point where either the derivative is 0 or it's not existing. We said that the derivative doesn't exist when we had this kind of crazy looking situation where we had multiple tangent lines that were all valid. Okay, since the tangent line wasn't unique, we can't really make sense of the derivative. So that was what we came up with so far. So what we were starting to build out was this process of identifying all of the mins and maxes of a function by first identifying every critical point and then classifying each critical point as a maximum, a minimum, or neither of those two things. Okay, that's what we were doing. So, once we know where a critical point is, how do we decide whether or not that critical point is a maximum, minimum, or neither? Well, what we kind of said is that if we are on a roller coaster going up and then we're going down, the logical implication is that somewhere in the middle we reached a sort of a high point. Okay, so going up and going down means in the middle we reached a peak. And so the way we describe this mathematically is by saying, well, what does going up mean mathematically? It means the function is increasing, which happens when the derivative is larger than 0. Okay, likewise for decreasing, that means we're going down, means the derivative is less than 0. So if the derivative changes from being positive to being negative, we can say with authority that there was a local maximum in between. If instead the derivative switches from being negative to being positive, that's what's going on down here, circled in blue, right? Goes from being negative to being positive, then we reach a local minimum. And if we go from being negative to being negative, well, we can't really say much. Likewise, going positive to positive, doesn't really mean anything. Okay, so what we were doing at the end of class was this problem number 7 here, where we were supposed to consider this polynomial function and find all the critical points and use the method we came up with in problem 6 to classify each critical point as a local max, local min, or neither. Okay, so let's see here. Where was I? So we found the derivative of f, and we said we know there's going to be a critical point when this derivative is equal to 0. So we set it equal to 0, and we solved for the x values which cause the derivative function to be equal to 0. So we got x equals 8 and x equals 2. These are our critical points. Okay, these are our critical points. They are candidates for potential mins and maxes. Okay. So, what we want to describe is, if I'm looking at my graph here of my function, I don't really know what it looks like, but I know I've got this point -2 and this point 8. I want to know how the derivative is behaving nearby these points, but not at these points. Okay? So, here's one thing I know. The sign of the derivative in between these 2 points won't change. Okay? The sign of the derivative won't change. And let me explain why. The derivative is a continuous function. It's kind of like a slider. Okay? You can think of it as like a little slider, and this thingy here can go up and down. And here's 0. If at one point we are above 0, and then later on our slider dips beneath 0, well, in order for us to move the slider from the top to the bottom, we have to pass 0. But we already identified that f prime equals to 0 only happens at -2 and 8. Okay? So, what is this all to say? This is all to say that if I use this number line to describe the sign of f based on given x values, then I will have a consistent sign in each of these 3 intervals. Because otherwise f prime would have to be 0 again somewhere else, in which case we would have found that the derivative would be equal to 0. But we already know there's only 2 times when the derivative is equal to 0. It's when x is equal to 8 or x is equal to -2. Okay, so what I'm going to do with this number line is describe the sign of f and try to identify whether the sign is going from like positive to being negative. That would indicate a maximum at -2, or if it went from being negative to being positive at 8, that would indicate that we would have a minimum at that critical point. So that's why I'm writing down this number line, is to try to identify how the sign of f is behaving. We call this the first derivative test. Okay, so what am I going to do with this number line here? What I'm going to do is, since I know that the sign of the derivative, so f prime is ... We're going to fill in the blanks for this spot, and then this spot, and then this spot, with either positive, negative, or 0, I guess, is an option. Okay. So, Since I know that in each interval, the sign of f does not change, if I want to know the sign of f in one of those intervals, the only thing I have to do is pick one point from inside each of them and plug it into my derivative function. If I get a positive number, then the derivative will be positive in that interval. If I get a negative number, then the derivative will be negative in that entire interval. Okay? So the numbers that I'm going to pick are -3. In between -2 and 8 is 0. 0 is always an easy one to plug in, so I like 0. And I'll pick, I don't know, I'll pick 10 from this side. So that's another one that's kind of easy to do. Okay, so what do I do now? I take my purple points and I plug into, I'm going to take my purple points and I'm going to plug them in for x in f prime. If I get a positive number, I know that f prime will be positive in that entire interval. So let's do it. I'm going to give myself a little bit more space here. Okay, so f prime of 3 is equal to 3 times 3 squared minus 18 times 3 minus 48. So that's equal to, let's see, 27. Oh, sorry, this should have been -3. 27 plus, let's see, 8 times 3, that's 24, plus 30 is 54. I think I did that right. Minus 48. Okay, so that's what we got when we plugged in -3 into our function. And, well, 54 is bigger than 48, so I'm confident saying that this number is going to be larger than 0. Okay, so we found out that f prime is larger than 0 in this interval. Okay, now I'm going to do the same thing with my other 2 points. I'm going to check what's f prime of 0. Well, f prime of 0 is just going to be equal to 0 minus 0 minus 48. That's less than 0. So I'm going to indicate that f prime is less than 0 in that entire interval. So any number that I pick between -2 and 8, if I plugged it in to the derivative, I would get a negative number. Now I need to check my last one, 10. I wish I had a little more space on these problems. F prime of 10, well, that's going to be equal to 300 minus 180 minus 48. I think, again, this is going to be larger than 0. Okay, so now we know how f prime behaves in each subinterval. We can decide whether we think x equals -2 and x equals 8 correspond to local minimums or local maximums. Okay? So let's focus on -2 first. We see our derivative to the left of -2 is larger than 0. That means our function is increasing. So our function might look something like this here. And then in the middle, we have our function has a negative derivative. That means we're decreasing like this. And then the last part, we're larger than 0 again, so we're increasing. So, -2, what do we think? Local min or local max, or neither? Yeah, what? Yeah, it's going to be a local max. How about 8? Yeah, it's a local min. Very good. Okay. So we have a local max at -2 and a local min at 8. Any questions about this number line stuff? Well, if you don't like the number line, you're in luck because I'm about to describe another way that we can do this that you might like better. So, let me go back up to this thing, this graph here. I'm going to erase all this jazz. And I'm going to see if we can come up with another way to tell whether a critical point corresponds to a local min or a local max. Okay, and it has to do not with the first derivative, but with the second derivative. There's a reason we call the first derivative test the first derivative test, right? There's a second derivative test. So, aside from describing, okay, am I starting up, going up, and then going down? That means there's a max. There's another property which characterizes maximums. And it has to do with the concavity of our function. Right? In this yellow square, do we think that we are concave up or concave down? Yeah, it's concave down, right? Because this kind of looks like an N. Okay? So we're concave down here. In our minimum situation, this kind of looks more like a concave up situation. Okay, that's the other way we can tell whether something's a minimum or a maximum. Okay? All right. So let's make it rigorous. So our critical points are x equals -1, x equals 0, and x equals 1. Now, I know that f of x is equal to 3x to the 5th minus 5x cubed. In fact, I also computed f prime of x last time. We got 15x to the 4th minus 15x to the 2nd power. And we can even compute f double prime of x. That's going to be equal to 60x cubed minus 30x.
How did you get 60 and 30?
The question is, how did I go from f prime to f double prime? So on each of these two terms, I used the power rule. So the 4 got multiplied down front, so 60 came from doing 4 times 15. And then the power was reduced by 1, that's why the new power is 3. And then the other one, I took the power rule again. The 2 came down front, I did 2 times 15, that's how I got 30. And the power reduced by 1, that's why I wrote x. Thank you for asking. Okay, so now we have the second derivative. Now, remember, if we want to describe the concavity of our function, The concavity has to do with the sign of the second derivative. If the second derivative is positive, what will my concavity be? Yeah, what?
Concave up.
Concave up. Very good. If the second derivative is positive, we'll be concave up. Second derivative is negative, we'll be concave down. So let me write that. F double prime greater than 0, that means concave up. F double prime less than 0 means concave down. Okay, so we can figure out whether x equals -1, x equals 0, and x equals 1 are maxes, mins, or neither just by looking at this second derivative. So let's try f double prime of -1. Well, we'd get -60 plus 30 equals -30. So we have f double prime of -1 is less than 0. This means the corresponding critical point, we're concave down at that point. And that tells us that x equals -1 is a local max. All right, let's try f double prime of 0. You get 0. Okay, so that doesn't tell us anything. And f double prime of 1, we'll get 60 minus 30 equals 30, and that's larger than 0. So that's telling us f double prime larger than 0 is telling us that we have concave up at that critical point, which is telling us that we have a local min. Okay, so let me write it explicitly, what's going on here. At a critical point, x equals to p, if f double prime of p is less than 0, we have a local max. Okay, so concave down corresponds to a local max. F double prime of p greater than 0 implies we have a local minimum. Okay, now remember, this is completely consistent with our understanding of like how we remember concavity, right? What I wrote was concave down looks like the n in the word down, and concave up looks like the letter u in the word up. Okay, so concave down, our picture is going to look like this n here, which looks like a local max. Likewise, concave up, our picture looks like this u here, which corresponds to local min. That is the second derivative test. Are there any questions about the second derivative test? Do people like the, raise your hand if you like the second derivative test better. Anybody like the number line better? Okay. Yeah, I use both. It really just depends on the circumstances. If it's really easy to compute the second derivative, it's usually worthwhile. But the number line will also never fail you. Okay, so that's it for this lesson. We're going to move on to the next one. and we're going to talk about the second derivative analog of the critical points. Okay, so the previous section we learned about critical points, what it means for something to be a critical point. It means that it's a candidate for potential max or min. Okay, candidate for a potential max or min. All right, so now we're going to talk about the meaning of f double prime equal to 0 or f double prime undefined. Okay. So, we've already actually talked a little bit about what this means. Does anybody remember the word that we had for when our function changes concavity? Kevin, you remember it?
An inflection point?
It is an inflection point. We said that an inflection point is when the concavity of our function changes. Okay, so yes, okay, so that's what we're going to do here. First of all, let's have a little bit more practice with the second derivative test. Okay, so if I were to find the points on this graph which have the derivative equal to 0, i.e. the tangent line is horizontal, it'd be at this point negative 2, and at this point positive 8. Okay? So, if we want to know whether these correspond to a local max or a local min, we can use the second derivative test to verify that the second derivative is positive for a local min or negative for a local max. So let's do it. If we have f prime of x equals, let's see, it'll be 3x squared minus 18x minus 48. Then f double prime of x will be the derivative of that, which will be 6x minus 18. So f double prime of negative 2 will be equal to negative 12 minus 18 equals negative 30, which is less than 0, which implies that the point negative 2, comma 104 is a local max. Likewise, we can try with f double prime of 8. What are we going to get? 6 times 8, that's 48. Minus 18. We get positive 30 this time, which is larger than 0, which tells us that the point 8, comma negative 396 is a local minimum. All right, so that's the second derivative test for us. Okay. So now let's consider part B. We want to understand the intervals on which the function f appears to be concave up or concave down. Let's think about that. I'm going to erase this stuff so it's a little bit more clear. What do we think? Where are we concave up? Can somebody give me an interval on which we're concave up? Yeah, so from 8 and to the right, this part of our graph is certainly concave up. That looks concave up to me. Any other places where we're concave up?
I'm sorry, 3 and negative 146.
Yeah, so the concave upness sort of extends all the way until we hit this point 3. How about this section here? What do we think? Concave up? No, concave down. Okay, so this is the extent of where we are concave up. And we'll use a different color to describe the place where we are concave down. And what happens right in the middle is called an inflection point. Okay, what happens in the middle is called an inflection point. To the left of this purple line, we have f double prime less than 0. To the right, we have f double prime larger than 0. What do we think happens at this point 3?
Increases.
It is increasing. What's the value of f double prime?
0.
Should be 0, right? If I'm negative, 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 and then suddenly a split second later I'm positive, I must have hit 0, right? It's like my slider. I got to go past 0 to get to the top part of the slider, okay? All right. So on what intervals does the graph of f appear to be concave up? Well, we could write this interval as, so concave up, our interval is going to be 3, comma, I don't know, infinity maybe. Concave down might be like negative infinity, comma,
2.
not negative 2. If we go to negative 2 here, that's to say that everything to the left of this orange line is concave down, which is true, but it's not quite the full picture. Where should I put the orange line instead?
0.
Hmm? Not at 0. At 0, if I put it here, it would still cut off a little bit of that blue section. I want the line to divide the blue section and the orange section.
Second one to 3.
Yeah, it should be at 3. So we're going to go from negative infinity all the way up to 3. So we're concave down. Okay? So I've characterized the concavity of our function on the entire real line except for one point, right? Neither of these intervals include the point 3. So the last thing I might say is f prime is equal to 0 when x is equal to 3. Something like that. Okay. Let's verify that that's true, by the way. We already computed the second derivative of f. We know that f double prime of x equals 6x minus 18. What's going to happen if I plug in f double prime of 3? Well, I'm just going to plug in 3 and I'll get 18 minus 18, and I get 0. Okay, wonderful. This is consistent with everything we've said so far. Okay. We want to find all values of x such that f prime of x, which is equal to 6x minus 18, is equal to 0. Are there any other values of x that cause this to be true other than 3? Yeah, no, there's no other values of x that we could plug in here. The only thing that we can plug into the equation 6x minus 18 and get 0 is the number 3. Okay? In other words, lines only have one horizontal intercept, right? Well, they come up, they cross the x-axis, and then for the rest of their life, they move on. Okay. All right, based on our observations in part B and our answers in part C, can we guess the relationship between concavity of a function f and points P, where f double prime of P equals 0, or f double prime of P is undefined? Yes, we can. All right, what do we think? If f double prime is equal to 0, let me pose the following question. If f double prime is equal to 0, do we have an inflection point? Is it possible for us to not have an inflection point? I see McLaren shaking her head. Yeah, if we can remember about 5 minutes ago, when we did this problem here, we found that f double prime of 0 was equal to 0. Actually, that's a bad example. This is an inflection point. Dang it. Okay, I messed up my example here. It doesn't necessarily mean that there is an inflection point, and here's why. What we can have is, for example, a function which is, say, concave up at the start, comes down, flattens out for a split second, and then goes back up to being concave up. So in this point here has f double prime of P equals to 0. Okay, but the definition that we have for an inflection point is a point at which the concavity changes. Okay, so f double prime of P equals to 0 and f double prime of P dne are, I should say, imply P comma f of P is a candidate for an inflection point. If the concavity changes sign at P comma f of P, then we've got it. It is an inflection point. Okay, so this illustration on the right-hand side here was to say that f double prime equals to 0 is a necessary but not sufficient condition for an inflection point. Okay, an inflection point is where our concavity changes sign. All right, let's find the inflection points. Do I have time? Yeah, I do have time. Let's find the inflection points of this function here. Okay, so we're given a function. We don't even know really what its graph looks like. So we're going to need to be a little bit careful here. Okay, we're going to have to be a little bit careful here. First, we're going to need to find our candidates. Once we have our candidates, we will need to check this condition. Namely, does the concavity change from one side to the other? Okay, does the concavity change from one side to the other? That's what we'll need to check. So the first thing that we'll need to do is compute the derivative of g of x. What are we going to get? Power rule 4x cubed, power rule 3x squared, power rule 6x, constant rule plus 0. G double prime, we're going to get 12x squared minus 6x minus 6. And our goal is to understand the candidates for inflection points. We know that candidates for inflection points will be when this function is equal to 0 or it doesn't exist. Like with the first derivative, we don't need to worry about the second derivative of a polynomial existing or not existing at a given x value. Okay? Polynomials are nice and smooth, and if you'll notice something, you'll find that the derivative of a polynomial is always a polynomial. And then the derivative of that will again be a polynomial. Okay, so polynomials, we're all good to go in terms of the DNE thing. We don't really need to worry about that. So we're going to check when this is equal to 0. Okay, well, I can divide the entire thing, both sides, by 6. I'll get 2x squared minus x minus 1 equals 0. We can factor this. We should have a plus 1 and a minus 1. I think the minus 1 should go with the 2x. And then we should have just x here. Okay, so we factored that guy. Now we just solve each of these individually. This means that x is going to be equal to negative 1/2, or x is going to be equal to 1. So, these are our candidates. To check whether or not our candidates are going to be inflection points after all or not, the process that we're going to take is going to be similar to the process that we used for figuring out whether or not critical points were maxes or mins using the first derivative test. I.e., we're going to use a number line again. So, here's negative 1/2. Here's 1. Since inflection points are points at which the concavity changes sign, I'm going to check whether or not f double prime is ... larger than 0, less than 0, equal to 0. I know it's only equal to 0 at -1/2 and 1, which means that f double prime will remain consistent in each of these intervals. Okay, f double prime will remain consistent in each of these intervals. So we can choose a test point from each of them. I'm going to choose the test point -1, the test point 0, and the test point 2. Now what are we going to do with these test points? We want them to inform us of the sign. That should have been a g double prime. The sign of the second derivative in each of those intervals. So I'm going to take -1 and plug it into g double prime to figure out what is the sign of g double prime in that interval. Okay, so let's do it. G double prime of -1 is going to be equal to 12 times -1 squared, that's just 12, plus 6 minus 6. So that's 12, which is larger than 0. So we know that g double prime is larger than 0 in this interval. Let's check what's going on with g double prime in the next interval. We'll use our test point 0 to check. G double prime of 0, that's going to be equal to 12 times 0 is 0, plus or minus 6 times 0, minus 0, minus 6 equals -6, which is less than 0. So we know that in this interval here, g double prime is less than 0. Now, in the last interval, we'll try g double prime of 2. We'll get 12 times 2 squared. That's 12 times 4. We'll get 48. Minus 6 times 2, that's 12. Minus 6, that's 48 minus 18, which is 30. Larger than 0 again. Okay. Question for the class. Can we confirm that the candidate x equals to -1/2 is indeed an inflection point? Hearing no, does anybody disagree? Seeing some nods, yes. What did we say was important for a candidate to pass the inflection point bar? The concavity needs to change sign. If the concavity changes sign, the derivative of the derivative should go from being positive to being negative, or from being negative to being positive. Do we see that happening here? Yeah, we do. First it was positive, then it was negative. So in between, we have a critical point. So this is a critical point. How about the other one? X equals to 1. Can we confirm it? Yeah, I think so. It's also going to be a critical point. So x equals -1/2 and x equals 1 correspond to inflection points. Shit, have I gone over? I have gone over time. Okay, sorry. 1 minute passed. You're free. If you want to stick around after and get a little bit more practice, you can. Otherwise, have a great day.
I'm just looking for YouTube, and I couldn't find the one that the extra slip that was due for today. What video is that one? Or what date is that one?
So, what day is today? There's probably no exit slip due today because...
There is. There's one there's due one today.
I know there was one I had to extend because I had to spend an extra day on chain roll.
Mm-hmm. Oh, I thought there was one that was due today. I just want to make sure. I think it might have been the 3.3 or something like that.
Yep, no problem. Have a good one.
Or not 3. It's 3.4.
Hang on. Let me check my thing real quick.
I'm a bit confused of what my grade is. You're telling me